So this is our final week of class before the final exam. So this is posted on the weekly schedule, the course schedule here. But our exam is next week, Thursday, 8 a.m. to 9:50. So a little bit different time, so careful of that. But in this room right here, A2111. Okay. So it'll be just like the first exam where it's paper and pencil. You can bring a basic calculator or, a graphing calculator is fine. Just no smartphones, no computers. Yeah. And so for that, I posted under weekly content a list of final exam review concepts. So there's not like practice questions, but this is a list of topics as like a checklist for you to go through, okay, for each of the different areas we've covered so far. My suggestion for reviewing for the exam would be to go over the homeworks. Those are probably most relevant, and then in-class activities and SAS activities as well. And then the weekly readings, right? But I listed the concepts here to serve as a checklist to help you maybe with studying. You can use a cheat sheet here. Okay, so standard computer paper. Yeah. So any questions? Yeah.
So this isn't technically cumulative, like obviously we're gonna be like giving concepts, maybe we learned earlier, but based on like computer content lines, it's not.
So it's cumulative. Yeah, it's cumulative, but it will be more heavily focused on the later sections of the course.
Got it.
Yeah, but I can tell you for sure there will be stuff from early on.
Okay.
Mm-hmm. Yep. Any other questions about the exam? Feel free to email me if you have any other questions that you run into. Okay. Today we'll be talking about something that's not covered on the exam, categorical predictors and dummy variables. So under week 15, miscellaneous topics, sometimes we get to interactions in linear models. We didn't get to that this semester, and we're not going to, but I posted, if you're curious, I posted a handout from, I taught this class last summer. And so I have an activity on linear models using a data set on possums. And then I had a video going over that activity. So if you're curious about learning about interaction terms, although this is not covered on the exam, that's posted and available there. This is also not something we're going to be covered on the exam, categorical predictors. Okay, but we're going to go over it today because it's an important concept. I just didn't want to put it on the exam since you hadn't had a chance really to see that on the homework at all or get feedback on trying it out. So, all right. So I would still encourage you to follow along with this. And complete this. I'm also not making it an activity that you turn in this time for this one either. So this is just learning for the sake of learning. Okay. So we've only talked about quantitative predictors so far in the class, okay, for simple linear regression and multiple linear regression. But I mentioned how you can use explanatory variables that are categorical in linear regression models. Okay, so actually ANOVA, if we, although I'm in the Zoom meeting, so I guess I'll stick to here. So ANOVA, we have, let's see if I gave the linear model formulation of the ANOVA model. Not sure that I did. I did, okay. So ANOVA way back when, we talked about how you can formulate the one-way ANOVA model in terms of a linear model, like this. Okay. Which looks very similar to a, this looks very similar to a regression model, actually. And that's not a coincidence. That is because one-way ANOVA is a specific case of a regression model, actually where you have a categorical predictor as your explanatory variable. The results you get from both of them are equivalent mathematically. They're the same. I think just ANOVA, from my understanding, it's just ANOVA, that approach of solving the problem, thinking about it from an ANOVA perspective was a little bit easier to do, maybe by hand, than a regression with categorical predictors. Okay. But I feel like nowadays, computers have made regression so simple because we just call it in SAS or in R, something like that, just say fit a regression model. Doesn't really matter that it takes more computing power or more steps now because it runs almost instantly for us either way. So long story short, if you know regression very well, you can do everything you can do with one-way and two-way ANOVA because there's equivalent regression models for it. Okay. So we'll be talking about how exactly you can use categorical predictors in regression like this. And please ask questions at any time if you're curious or want to clarify anything. So as a quick review, simple linear regression, as a reminder, we're modeling a response variable, that's a quantitative variable y, as a linear function of predictor variable x. Okay. So if we're thinking about like the Palmer penguins data, for example, okay, where we had all these variables on different penguins, we can model a penguin's body mass using its flipper length. Okay, so body mass is equal to some constant intercept term plus their flipper length times a slope plus an error. Okay. So this is the type of relationship that we get. One quantitative predictor, one quantitative response variable, right? And we can use SAS to get a line of best fit, all right, through this data, right? Something like that. And SAS uses calculus to find what's called the ordinary least squares solution. Okay. Essentially the intercept estimate and slope estimate that find us that line of best fit through the data. Okay. And it does that by minimizing, again, using calculus, the sum of squared errors term. Okay. So if you think about this as like a function, so who's taken calculus in here? Assume most people, right? Okay. So when you have a function in calculus, we learn how we can take the derivative of a function, right? Okay. So you can rewrite the sum of squared errors as this function of the data. And then if you view y, the response values that you got from the data as like fixed constants, you can take and same with x, you can take the derivative of this quantity with respect to the intercept term. You can also take the derivative with respect to the slope. And then you find where the derivative is 0. Which would give us, so what does it give us when the derivative is 0 of a function? Most of the time. Maybe I remember. So like, I guess. Like let's assume. Okay, so we have like our intercept term, and then we have sum of squared errors. Okay. And then it's going to look something like this. Where is the derivative 0 at on here for this function? The bottom of the curve, right? Like right here. Okay. So if we find where the derivative is 0, it's where it's minimizing the sum of squared errors, right? It could be like a like the opposite, like a hump rather than a U shape, but this is how the SSE will look for regression. So when you find the derivative 0, that gives you the value of the intercept that minimizes it. Okay, so that's kind of what SAS is doing underneath. Finds where the derivative is 0, gives us that, and it does the same thing for this slope at the same time. You don't have to worry about that though, because SAS does that for us. But honestly, it's not too bad. There's like a nice solution for it. Okay, we end up with these numbers, right? And then we've seen how we can interpret the intercept and slope, right? So for the intercept, okay, there's our blueprint interpretation, and then for the slope, we have this blueprint interpretation. Okay. So here, for example, we're talking about we're modeling the body mass of the penguins using their flipper lengths. So we'd say for every 1 millimeter increase in flipper length, we expect a penguin's body mass to increase. And this phrasing "we expect" is important to convey that it's on average, essentially, to increase by 50.2 grams, comma, on average. Okay. That's how we can interpret the slope, right? What about the intercept? Anybody want to help us out there?
Their flipper length is 0, the body mass is negative 5,370.
Yeah, we'll say like the expected body mass of a penguin with no flippers. Minus 58.72, yeah. Yeah, well, and is that a good interpretation? Right. So yeah, we'll note the intercept should not be interpreted here, since this is extrapolation. And also a negative number is not sensible. That happens decently often with the intercept term, so. So that's all we should note here for the intercept. So that's all review. We've already talked about that for simple linear regression for a quantitative predictor, right? The solution there. But what if we wanted to incorporate categorical information in the model? Okay. So we talked about here how SSE, the solutions for these betas, right, is found using calculus with calculating a derivative, right? But if we have like the species of the penguin, right, being Gentoo or Adelie, right? We know that's important information for determining their body mass. These species have different body masses on average quite a bit. But how can we incorporate this text information into our regression model when we take like a derivative, which is all about numbers? It's a numerical algorithm, right? Anybody have any ideas? Yeah. Yeah, we can encode them or represent them using numbers, right? So right here we see, for example, that there is differences based on, yeah, we can look at species. We can also look at the sex of the penguin. There's definitely differences in the average or typical body mass between male and female penguins here. Okay. Which we can note here real quick, I guess. So which group had larger body masses here on average? Does it look like male penguins, right? Yeah. So yes, male penguins have larger body masses. Important to include on average, because there's some individual females that have larger body masses than males. It's just on average. Okay, and then talking about, wow, there's a whole page of space there. Okay. Right, so talking about how we can use categorical information, we essentially need to reframe the problem into something that we know how to do. Okay, mathematicians and statisticians notorious for this, and I feel like this is everything in like more advanced statistics and math, is always breaking down problems into easier problems that we already know how to do. So we already know how to handle quantitative predictors. So we can just reframe categorical predictors as that same thing. We rewrite them such that they have a numerical representation. One way to do this is to use what are called dummy variables, which is I say one way, I guess this is the way in which people do this for all types of models. So linear regression, you know, even if you get into more advanced predictive modeling, like neural networks, or like what ChatGPT is based on, right? Like it's based on a lot of text information. Everything underlying that involves numerical algorithms. So it needs to like encode text in a numeric form at some point. Okay. And some of how it does that is using dummy variables. So the dummy variables, also called indicator variables, are binary variables. So they take on a value of 0 or 1 that indicate whether or not an observation belongs to a group. In order to represent a categorical predictor with L sub k levels or L sub k groups, you need L sub k minus 1 dummy variables. You might think, like, if there's 3 species, you need 3 dummy variables, but you actually only need 2. Because, for example, or let's talk about, yeah, the sex of the penguins first. Okay. Here's a dummy variable indicating whether the penguin's male or female in this data set. So 0 for male, 1 for female. Because there's only 2 categories, you only need 1 dummy variable to tell us if the penguin is male or female. Because if we know it's a 0, it has to be a male because there's only 2 categories here. And if we know it's a 1, it has to be female. And that continues on if you had more categories. You know, for species, you would need 2 dummies because you could have an indicator of it being a deli, an indicator of it being a chin strap penguin. And if it's neither of those, then you know it must be Gentoo, for example. So we avoid redundancy in how we encode the information. But that's how we can use dummy variables or indicator variables to encode categorical information. In machine learning, I learned this after grad school, reading blog posts about machine learning stuff. They like to call this one-hot encoding your data, essentially converting categorical information into a numerical representation. I feel like it sounds much fancier than it is. Rather than dummy variables, they always say like, "Oh, do you know how to one-hot encode your data?" Though sounds way cooler. That's machine learning. I feel like it's just a flashy representation of statistics that has always been there anyways. But so when we make these dummy variables, because you have 1 less dummy variable than the number of categories, there's 1 category such that all the dummies are equal to 0. The one that's implied when all the dummies are saying, nope, not that group. And that's what we call the baseline or reference category. Okay, so it's the one that does not get its own indicator or dummy variable, that group. So for example, here, what is our baseline category for the sex variable? It's males, right? Or the reference category here. You could have encoded it differently. It will just change how you interpret the results of the model, but you'll get the same answers either way. So, okay, so some examples where this is very useful. If you're predicting, say, how many points a basketball team will score using regression, it's a known characteristic about basketball games. If you look at it, teams playing at home, for example, in college basketball, score about 2 to 3 more points on average than, or actually like 4 to 6 points more on average than when they're playing away. Okay, they play a little bit better at home. So this is categorical information that we could encode in a predictive model for basketball games, where we would need a dummy variable indicating if they're home, a dummy variable indicating if they're playing away, and then teams can also play on a neutral court. Essentially, neither team is home or away, and that could be the reference or baseline category. Yeah. We could also have, in like a clinical trial setting, you can have your drug maybe you're considering using. an alternative drug, maybe the current standard of care, and then a placebo. Okay. In that case, you could use a regression model with treatment group or drug assignment as a explanatory variable. In this case, typically what you do is you would make like the placebo group the baseline or reference category, just to facilitate interpretations of the effects, because then you get an effect of your drug, a slope corresponding to this effect essentially, and a slope corresponding to the current practice above just using a placebo. So sometimes the reference group, like which one you set as the baseline or reference category, is important. Other times it doesn't matter. Like in this case, you could have set the males or females as the reference group, and it really would be fine either way. Either way makes sense. But sometimes it makes more sense to do one group than another. So notice like this is a setup that very much resembles one-way ANOVA, okay, where we could maybe be comparing average blood pressure between these three groups. Okay. And you could certainly use a one-way ANOVA. If you fit a regression model, if we fit a regression model where it's y is equal to an intercept plus this. Okay. You could have a regression model just like this, where x1 is an indicator or a binary variable to indicate if the patient was given drug A, x2 is an indicator variable, or if the patient was given drug B. This is your linear model where y is their blood pressure. This is equivalent to a one-way ANOVA model, actually. Okay. So people do still use one-way ANOVA a lot in practice, but also some people just use regression because it can be easier to control for other factors like demographic characteristics about patients or things like that. So we'll just start with a simple example here where we're looking at encoding the sex of the penguin as a dummy variable here to use in a model to predict their body mass. So now in this case, with just one categorical predictor, in this case, the female indicator, okay, this is a simple linear regression model where x1 is 1 if a penguin is female and 0 if it's male. So you always need to define what your 1 and 0 represent for the dummy variable when using those in regression. Okay. It's important to clearly communicate that. Okay. And what does this imply about our predicted values? Well, if we look at the data here, okay, so we're plotting, here's all the body masses for the male penguins. So the indicator is 0. And here's all the body masses for the female penguins, where the female indicator is 1. Okay. So this is a way to visualize the dummy variable that we've created. If you look at the green line here, which is the average, it's right at the average male body mass, and the blue line here, which is right at the average female body mass, okay, you can see this difference in height. That is given, why is this doing that? That is given right here by the slope that ends up showing up for the indicator variable, actually. Okay. This difference is 683. Okay. So by using a dummy variable, acting like it's a quantitative predictor, which it is, and getting the slope for it, that's how it shows up graphically when you just had two categories. It's the difference in the heights of the averages between the groups. Right, so which group is the baseline or reference category here? We already said that actually. The males, right? Male penguins are the baseline reference category. Okay, and then how do we interpret the slope? Okay, so the slope here, so since the estimated slope is this, what does that mean? Anybody want to help us out with that?
So when a penguin is female, you subtract 682.4 from their average weight.
Yeah, that's
Average weight.
right, the expected average weight. So yeah, female, we can say it, female penguins, we expect female penguins to have body masses that are 683.4 grams lower than that of male penguins, comma, on average. That's how we can interpret that effect. So whenever you have categorical predictors, how you interpret the slopes for the dummy variables is always in comparison to the reference category. In this case, it's like we expect female penguins to be this much lower than the baseline group males. Okay, if we think about, so the intercept is always setting all the predictors to being 0, and then that's our expected value. So if x1 is 0, y hat, or the expected value, is this. Since the estimated intercept is this, the expected body mass of, and then which type of penguin is it for the intercept? Right, of a male penguin is 45.7 grams. This is exactly the same as if you just calculated the average weight of the male penguins in the sample. That's exactly what this number is. And it shows up in the regression model that way. Okay. So again, has a very nice interpretation. How could we get the expected body mass of a female penguin? Well, we can just, that's a predicted value, essentially, is what this is asking for. Okay, so we can take our estimated regression equation, think about when a penguin is female, for a female penguin, what do we put in for x1? We put in 1, right? So we do times 1, and that gives us this number, which is exactly equal to the sample mean body weight for the female penguins, if you calculated that out. And we already said this, expected body mass of a male penguin is the estimated intercept. Any questions about those? How we interpret the estimated slope and intercept? Okay. It's not too bad when you just have two categories. Here, let's look at how we can visualize this data again. So again, we have this dummy variable, this indicator variable for the penguin being female or not. So we can plot it as if it's all quantitative in a scatter plot like this. You end up with this funny looking, a lot of overlapping points because there's only two unique values for the indicator. Okay. Another way to view how the slope estimates come about, okay, is again viewing it as if it is just a simple linear regression where we're fitting a straight line. Okay. So SAS, taking everything's quantitative, just gives us a straight line of best fit between the points. Okay. The slope of this line that is connecting the two groups of points here is exactly equal to the estimated slope in that regression equation. And then the y-intercept for this line gives the expected body mass of the male penguins, the average body mass of the males. Okay. So yeah, there's a lot of things going on in this plot. You have that slope that shows up, the y-intercept, also the point at which it connects each of the two groups here is the sample means for each group. Okay. So right where it touches right here, this is the sample mean body mass for the males, and then right down here is the sample mean body mass for the female penguins. Okay. So that's another way to view it where it's still just a regular simple linear regression now. Okay, with just nicely interpretable aspects about it. And so that was just a categorical predictor in the model. We've seen multiple linear regression with multiple predictors, right? So just like before, we can encode or use several predictors in our model. So maybe we want to use the sex of the penguin, but also their flipper lengths to predict their body mass. So we can do that. We have the indicator variable now for the sex of the penguin, and then we have the flipper lengths also as a predictor. And we use SAS again to get estimates for that. Okay. And now here's our implied set of predictions. So you can see the green line and the blue line. So very similar to what you would get here if you just fit a model with flipper length, but now it's shifted vertically for each group. You get a little more accurate of a prediction if you knew that the penguin is male. It's a little bit higher body mass given its flipper length and a little bit lower for the female penguins on average. So you get a little more accurate. Okay. Note that in this type of model, okay, where you have an indicator for the sex of the penguin and then one predictor for the flipper lengths, these two lines, they're shifted vertically like this, but they're constrained to be perfectly parallel. They have exactly the same slope, in other words. Does that look like that's fitting the data well here, having the same slope for each group? It's actually not too bad. It could be a little better, but so here it looks okay. Like if we imagined if all the blue points were missing and it was just like, that's our line of best fit. Like, how does that do? Well, it looks pretty good. And same with the blue group. So that seems fine. Sometimes you have like an extreme case though, where it is possible, like for some reason, for female penguins, it's like really positive. And then it could be for male penguins, maybe for some weird reason, as their flipper lengths get bigger, they get smaller body masses. That could be the case. In which case you would see that like the fits don't look very good at all when you plot it like this. That's actually the case. If you want the slopes to differ by the group that you're in, that's where you need what we call an interaction term in the model. And that's where that other activity that we're not getting to talks about how you can include interaction terms to allow that. Okay. But here, we're just considering the simple case where the lines are constrained to be parallel. Okay. So that was looking at how we can use a categorical predictor with two groups in it. Okay. There's also this species variable in the data set where there's 3 different species. The penguins can be a deli, chinstrap, or gentoo. Okay. So to use that as a predictor, okay, we would need, how many dummy variables would we need to encode that information? 2, yeah. So since there are 3 species, we need 2 dummy variables to encode the species information in a model. So using just species, it's only 1 variable, but now to use it in a model, that results in 2 predictors. Okay, 2 dummy variables. So Y is still about a penguin's body mass. Now X1 is an indicator of it being a chinstrap penguin or not. X2 is an indicator of the penguin being a gentoo penguin or not. And then we don't have one for a deli because if X1 was 0, so not a chinstrap, X2 was 0, not a gentoo, we know it has to be an Adelie penguin. So we don't have that additional dummy variable. And so which one is then the implied baseline category for this model up here? Or which species?
Adelie.
Yeah, the Adelie penguins. Again, in this case, I would say that's not very important that they were designated as the baseline category. Unless you like have some reason that they're more important than the other species maybe or something. And then we'll say since they do not have their own dummy variable. Okay. And here's how the data looks. Okay, we never actually see this step because when you code it up in like SAS or R, you just give the categorical predictor. And what happens is the software underneath, it doesn't show you. Underneath, it creates dummy variables for you and then fits a linear regression for those. Okay, but here's what it looks like underneath. You have this indicator for chinstrap, 1 for chinstrap, indicator for gentoo. Notice it's all zeros except when it's gentoo. And now this is all numeric information that can be used with the optimization algorithm, calculating the derivative, getting the numerical estimates. Okay. And so that's how we do it here. Now visualizing this, so we fit this in SAS, for example, we get an estimated model. Okay. Here's where it looks like again. So now we have, and the x-axis isn't super important here, but it's representing the 3 different species. Should fix that label. We had the Adelie penguins, chinstrap, and gentoo. Okay, and then I drew a horizontal line at the sample mean here. Okay. So in the estimated model, notice that, okay, so X1 was an indicator of, let's see, okay, Adeli, green, Adeli is our baseline group, our reference category. Okay. Gen 2 is X2 right here. So see the effect of the Gen 2 penguins? It's like 1400. That is exactly equal to the difference in height between the red line here and the green line for the Adelis. That's how that shows up. It's the difference in their sample means. Then you'll notice for the chin strap penguins, okay, the chin strap is the blue group. It's really similar to the green, the Adeli penguins on average. They're nearly identical. So their effect was only 27, which on this scale is really, really small. Okay. But the difference in heights between these two lines, which is actually kind of hard to even see, is only 27 grams. And then we have the intercept. So what does the intercept represent here? The average, right? The sample average for the Adeli penguins is given by the intercept. Because for Adeli penguins, X1 is 0 and X2 is 0. So for every Adeli penguin, this is the expected or predicted body mass here. And just like before, how we included quantitative predictor along with all these dummy variables in the model. Okay, we did that when there was 2 categories. You can do that with 3 categories as well, right? So now we have X1 is an indicator of the penguin being chin strap, X2 an indicator being Gen 2, X3 is the flipper length. Okay, we can have all of that in the model now to predict body mass. And so when we look at that here, again, you end up with constraining the lines to be parallel within each group, and you get a separate, it implies essentially a separate linear regression line for each group. That's what this model corresponds to. And yeah, maybe or maybe not, but that's reasonable, right? You imagine taking away all the points except the green ones. Green line looks pretty good. That seems fine. Blue line also seems pretty good. The red line looks like it could be a little better, right? Like it seems like it should be maybe tilted more up. But it's also not the worst. And that's again, if you want, you can have the slopes vary within each group, but that would require including an interaction in the model. What's called an interaction between the flipper length and species of the penguins. Okay. Right. So yeah, talking about how we interpret the estimated intercept here. Okay, the estimated intercept can actually sort of copy what we put before, where we have that where did we talk about extrapolation? All the way up here. There we go. Okay. Same thing applies here, right? Because flipper length is a predictor in this very bottom model now. Okay. All right. Here's our estimated intercept. What does this correspond to in this case? even though it's not sensible in this context.
No.
Yeah, flipper length of 0, and then what else about the penguin does it correspond to? So this is 0 is the flipper length.
Oh, and then
And then it's an Adelie penguin, because this being 0 means it's not chin strap. This being 0 means it's not Gen 2. This being 0 means it has no flippers. Okay, so it's a Adelie penguin with no flippers. Okay. Or penguin. So it doesn't make sense because it's extrapolation. There's no, if we look at the data here with the Adelie penguins, okay, all of them had flippers. So that's outside the scope of the data set. Okay. So we'll say that no Adelie penguin had a flipper length of 0 millimeters in this data. And also, even if it was in the scope of the data, sometimes you can get negative numbers, even if it's not extrapolation, in which case you shouldn't interpret it like you would just say, oh, it's negative, so the predicted value is not sensible in this setting. Okay, yeah, what about each of the slopes though? All right, so let's see, beta hat 1 is this. So since the estimated slope for x1 is this, yeah, I'll interpret this first one. The expected body mass of a x1 was for chin strap penguins. So of a chin strap penguin is 205.4 grams less than that of an Adelie penguin on average. That's how we can interpret the first slope. Always good to double check by looking at the plot when you have it like this, right? So we're saying a chin strap penguin has lower body masses than the Adelie penguins. Is that what's showing up in the plot here? Yeah, that checks out. The blue line is below the green line. So always good to do a little bit of a sensibility check like that real quick. Okay, what about x2? So for x2, the estimated slope was 284.5. So the expected body mass of an x2 is the indicator for being a Gen 2 penguin. So expected body mass of a Gen 2 penguin is 284.5 grams more. Yeah, because it's positive. And again, we can see that that shows up in the plot. Like the Gen 2 penguins line is above the Adelie penguins green line here. And specifically, this difference in height between the lines is exactly equal to 284.5. Actually, I forgot. Okay. Yeah, we need to add a little bit to these interpretations here. Does anybody see what I forgot? So this would be good if species was the only predictor in the model. What do we need to add here? Yeah. If gender was the other predictor, yeah. And here we had flipper length, right? But yes, that's the idea. Holding the flipper length constant, right? It's an important thing to mention because, especially like in this context, if you think about comparing two penguins, okay, like one's a Gen 2 penguin, one's an Adelie penguin, they probably have different flipper lengths on average. So if you want to compare across species, you need to first find penguins within each species that have the same flipper lengths to isolate the difference of species, right? So this effect is after accounting for flipper length. Yeah, always important to specify that it's conditioned on the other predictor variables. Like in the clinical trial setting, that example where we were looking at the effect of the drug, for example, you might include like the sex of the participant or the age of the participant as additional predictors, because then you want to describe the effect of the drug after you remove the effects of age and sex of the participant, which might affect people's blood pressures in their own way. But we're interested in the effect of the drug, not the other things differing. Or in this case, we're interested in describing the effect of the species of the penguin, not so much as how the flipper lengths affect their body masses. And lastly, we can give the interpretation for x3. So x3 has a slope of 40.6. So since it's 40.6, how could we interpret that slope here?
Expected body mass of the penguin is 40.6 grams higher per 1 millimeter increase in bone.
Right. Yeah. So it's like the traditional slope interpretation for the most part. So we say for every 1 millimeter increase in a penguin's flipper length, we expect their body mass to increase by 40.6 grams on average, right, for a given species. For a given species, or in other words, holding species constant. Okay. Any questions about how we interpreted those values? All right. So then let's practice getting some predicted values. So what is the expected body mass of a chin strap penguin with a flipper length of 195? Okay, so let's copy our equation, our estimated regression equation. It's always a good place to start when getting a predicted value. Okay. Okay, so, and let's plug in, so what we need to do is substitute in the values that we know for x1, x2, and x3 now. So chin strap penguin with a flipper length of 195, what is x1 equal to then? Just 1, yeah, so times 1. What about x2?
0.
0, yeah. x2 is an indicator of it being Gen 2 or not. So this is a chin strap penguin. And then what about x3?
95.
Yeah, 195. Okay. So we can do that. And we'll use Google. Important to include the units and measurement on predicted values. Okay, so that many grams. So that's the expected body mass of a chin strap penguin with 195 for its flipper length. We can look at the plot that we had and see if that seems reasonable. So chin strap at 195, and we're saying it's about 3,700 grams. Okay. Let's see, chin straps in blue. 195 is like right here for their flipper length. Okay, let's look at the predicted value. It's like here. So is it like 3,800? That's 3,700. It's pretty close, yeah. Okay, so that seems like we calculated that correctly. Okay, so similarly, oh, and then is this extrapolation? Okay, so we got this predicted value, but was it extrapolation here?
No.
And why is it not, I guess?
Also in the prediction data set.
Right, like if we look here, 195 for a chin strap, which is the blue. There's a bunch of blue points around that area. So that's totally valid to get a predicted value there. Okay. Okay, what about a chin strap? Oh wait. Oh, okay, so that was our predicted value. Let's suppose we had a chin strap penguin that had a flipper length of 195 millimeters, and then we recorded its actual body mass. Okay, it's not going to be the same necessarily as our predicted model says, and it was actually 3,900. So what's our residual value then?
Just 3,900 minus 3,698.
Right, so residual in general is equal to, which this is important to know, even though we're going over categorical predictors here, which I said is not in the exam, you do need to know how to calculate a residual value for a regression model. Okay. So that in general is equal to actual minus predicted value. That's the formula for a residual. So here we get the actual was 3,900, and then the predicted was this. So yeah, it's about it's about 200, 201. So notice that the order of the subtraction matters, right? You'll get a negative, you can have negative residuals. A negative residual, like what would a negative residual imply about our predicted value?
Overestimated.
Yeah, it was too big. And then a positive residual means our prediction was too small. And the units are the same as the original variable, so grams. Any questions about that residual calculation? Okay. Then let's suppose we had a chin strap penguin who had really long flipper lengths, 225. Okay, so we plug in that into our equation, and pretty much we're just switching, instead of 195, it's 225. Okay. And then re-update that, recalculate that value using Google, right? Oh, is that right? Okay, sure. And then instead of 3,900, we get 4,900 grams. Okay. So at 225 here for the chin strap penguins. Okay. That's right here. So is that extrapolation? So yeah, key thing with multiple linear regression is that you have to look at all of the predictor variables and see if it's in that range of that combination of predictor variables. So what's tricky is almost without looking at the plot, it's kind of hard to tell. But looking at this plot, 225 would be fine for a Gen 2 penguin to get a predicted value for, but not for a Delian chin strap. That's actually extrapolation still. Okay. Which is tricky because we have data on Adelie penguins. We have data on penguins with flipper lengths of 225. But that's still extrapolation because that combination is not in our data set. Okay. And the problem, like practically speaking with it, is that here's the Adelie penguins. We can't assume that that trend continues for Adelie penguins if we saw like there was like some monster Adelie penguin with a flipper length really, really big. It might be that their body mass is like way bigger or way smaller than the trend would indicate. We don't know how that Adelie penguin would look necessarily. So yes, and again, this concept, like, yeah, we're going over categorical predictors here, but this concept applies to when we have only quantitative predictors as well. You need it to be in the range of both. Okay, so yes, this is extrapolation since 225 is above the maximum flipper length of the Adelie. I think we're, oh, chin strap. Wow, we finished this activity today. That's great. I guess we will get to the interaction activity. So next time. Although, okay, yeah, I guess we'll finish this last part before I talk about next class. So does it seem reasonable to constrain the regression lines? Okay, so we kind of talked about this. Does it seem like that's fitting the data well? Yeah, it's pretty good. The thing is, like, it seems nice to like, well, yeah, let the regression lines like vary within each group for the slope, because then you get more accurate predictions for this sample, right? But this is like a sample of data, right? Like we're getting an estimate of the slope, but it's not perfect because it's only some data. We don't have the whole population. The idea is if the slopes are the same for each group, by pooling them together like this, we're using all the data to estimate one slope. So we can maybe get a better estimate that truly is the same. If you break it out into all the groups always, you're breaking your data into smaller and smaller pieces and estimating more things. So your predictions might actually get worse for data that's out of sample. Essentially, it would be overfitting potentially. by allowing the slopes always to vary for every group. So it's like a trade-off again of like how complex you make your model versus how much you want it to fit the data well. That's a trade-off again. So you could use like adjusted R squared to help you decide if you should include an interaction term or not, which we'll talk about in that interaction activity. Okay, but here, yeah, I would say eyeballing this, I would say it seems fine. But also I can tell you, like, I would feel like the adjusted R squared here would tell you, I think it would like the interaction term. Mostly because of this Gen 2 group. I think it would want that slope to have its own for that group. So I wouldn't be surprised either if the data tells you to have a more complicated model. So long story short, yes, parallel lines fit the data reasonably well here. Okay. And the last thing I'll mention is that Dr. Allison Horst, who's a professor at, I think, University of California, Santa Barbara. So lucky her, that's like really nice weather over there. She made these really cool graphics about like multiple linear regression, which all involve these dragons, that talks about interpreting effects of categorical predictors. So like being a striped dragon or spotted. Talking about quantitative predictors, visualizing that. Okay. All these kind of concepts with regression, like we've talked about. She drew some nice pictures for it if you want to check those out. Okay. So next time, what we'll do is, since we have time, we'll go over this interactions handout. Okay. But I will, okay, it's our last class before the exam. I will allow, time at the start. Essentially, if you have any questions that you've come up with when going over the exam review concepts here, okay, I'll just take the time at start of class to go over those. Yeah. Yeah, so we'll still have class on, on Thursday. And if you have any questions, I'll essentially just keep answering them and we'll talk about it as much as you want. And then with the remaining time, we'll work on the interaction activity. So if you don't have any questions, we'll just work on the interaction activity the whole time. Otherwise, the more questions you have, the more time we'll spend reviewing, I guess. Okay. So it'll be up to you how much you want to do that, I guess. Yeah. And I'll post this video that we just recorded today.